Hello and welcome back to Tomography. So, let's see, what have we done so far? So thus far we've gone through talking about the radon transform, then we built up into the back projection, and then we did this sort of deep dive into the Fourier transform and the inverse Fourier transform, the Schwartz space, temper distributions, all this stuff. And there's a lot more I'd still want to say there. But we're at a good point where we know what the Fourier transform is, and we've been playing around with it for a little bit. And so so now we can leverage this experience and try to go and tie this back and bring us back on point with the radon transform. So what are we going to do today? I'm going to show you how the Fourier transform can be used in order to extract the original function from its radon transform. And so you basically can start from a sinogram, and then through a collection of operations, you can go all the way back to the original function. And so we start first by talking about the central slice theorem, which basically says you can represent a two-dimensional Fourier transform as a single Fourier transform on the radon transform of a function. And so and then after we do that, you can then build up to this relation that we call the filtered back projection. Now the filtered back projection allows us to use the inverse Fourier transform plus a couple of other little tricks in order to get the original function out from its radon transform. So so this is a great place to come back to the tomography lesson. And so this gives us yet another way of inverting the radon transform, and in addition to what we saw way back when we were talking about the back projection, way back when. And we'll conclude the lecture today with a sort of modern approach to what Radon did back in his original paper, and we will talk about how this is connected with the Hilbert transform. So anyway, so tune in with me, and we'll go ahead and get through it. All right, so we'll go ahead and start now. Okay, so at this point we've been talking about the Schwartz space and temper distributions and the Fourier transform on these. And that's taken a good 5 or 6 lectures, some of them being like a full 2 hours. So we've built up enough now that we can come back and talk about how some of these things are connected to the radon transform. Now we're not done talking about the Fourier transform. I still want to talk about the FFT and the Fourier transform of periodic functions and how that all connects back. But occasionally we should always touch back to the radon transform and tomography. So so the whole point was of all that was so that we can establish a couple of handy little theorems that allow us to change the way that we look at the radon transform and its inversion. Okay, so there are 3 quantities that we're going to be doing here, and here this is the chapter 2 big theorems, I think that's what it's called. Yeah. So this is chapter 6, 2 big theorems, and this is out of the book by Tim Feeman. Now when he starts this off, he actually isn't even mentioning the Schwartz space or anything close to it. He's mentioning a suitable function, but we went through the trouble of actually defining what exactly a suitable function is, and so so we'll be able to be a lot more specific than what he is. But to start off, we're going to introduce a little bit of notation. So just like before, we have F. So we have F, and this is going to be the Fourier transform over functions of a single real variable. So we're thinking of its domain
as, say, something like the Schwartz space of R. Then we have F2, and this is the Fourier transform over functions of two variables. Okay. Now, before we haven't really distinguished these two, but they're both going to be appearing in the same equation, so we want to be able to distinguish exactly what's going on. And if you, and so basically the regular Fourier transform of a function f evaluated at some point omega is 1 over the square root of 2 pi times the integral from minus infinity to infinity of f of x times e to the minus I wx dx. And then we have f2 of another function, let's just say g of w, so the Fourier transform of a two-dimensional function is 1 over, say, the square root of 2 pi and then squared, so just 1 over 2 pi times the integral over R2 of g of xy times e to the minus I omega transpose times xy, if you like. And this is, say, dx dy. So I could, instead of saying integral over R2, I can just put integral from minus infinity to infinity, minus infinity to infinity, right? So that would be the Fourier transform for a two-dimensional function. And of course, we should bring this back, the Radon transform. So we have the Radon transform of, say, a two-dimensional function, say Radon transform of, say, g, evaluated at, say, t theta, is equal to the integral from minus infinity to infinity of g of t cosine of theta minus s times sine of theta, comma t times sine of theta plus s times cosine of theta and ds. Right. So these are the three transforms that we are working with, and so the idea is that we would like to see how they are intertwined so that we can possibly exploit them in order to invert the Radon transform. So the theorem 6.1 is where we're starting out of the Feynman book, and it's called the central slice theorem. Okay. So it says for any suitable function f, such as f inside a Schwartz space, and this is of R2, and all real numbers, here we have capital S and theta. We have this, the Fourier transform of a two-dimensional function f evaluated at s cosine of theta comma s sine of theta is equal to the Fourier transform of a single variable function, and here we're saying Rf s comma theta. Let's see. Yeah. So when writing this, we know that the Fourier transform of a single variable function is actually going to give you a single variable function itself. So keep in mind that this Fourier transform I think my battery right now. All right, so this in particular is just the Fourier transform with respect to the first variable here, because this is the Fourier transform of a single variable function. So basically we would just fix this theta and let RF be just a function of S. And so, or a function of T is what usually goes in here, right? And so then here we using S as the frequency, and that would be the Fourier transform with respect to the first variable of RF. Okay, so that is the central slice theorem, and this is one of the fundamental bits that lead us to the ability to invert the Fourier transform. The first step is going to be to prove this, and then the next one is going to be the proof of filtered back projection giving us the original function back. And then those will give us strategies to approach inversion numerically, because we don't have a continuum of points that we've sampled. We only have a finite number of points we've sampled. So we're going to leverage those to the best of our ability to do Fourier transforms and whatnot. And that involves an algorithm such as the FFT, the fast Fourier transform. Okay, so let's go ahead and go through this proof, and we'll start talking about it. So proof. So here, given f, and we'll just say it's in the short space of R2, and we're going to have real numbers s and theta. We have this f2 of f evaluated at s cosine of theta, s sine of theta is equal to 1 over 2 pi times the integral from minus infinity to infinity, integral from minus infinity to infinity of f of x y times e to the minus I, and it's going to be s times x cosine of theta plus y cosine of theta. So this is just taking the dot product of this with x comma y. Alright, and so this is integrated dx and dy. Now, if you're following along in the book, you'll notice that we're doing 1 over 2 pi, and the book has nothing there. So this choice of constant that we took is a symmetric choice, and the book does talk about it a little bit. He prefers to have a clean Fourier transform, but a dirty inverse transform. I prefer to have symmetry between the two. But it doesn't really change anything substantial about the calculations, just the coefficient that's hanging out in front of them. Okay, so now we're going to try to do a change of variables. So right now, we're doing from xy, and we're going to go ahead and try to change it to what we're going to say is ts. So here, what we have is that we're going to start with t being what we have been looking at before, which is going to be x cosine of theta plus y sine of theta. All right, and so this is exactly the line that we saw before. And what we're going to do then is we're going to also select s to be minus x times sine of theta plus y times cosine of theta. Okay. Now if we go ahead and consider the Jacobian, the Jacobian is just going to give us dx by dt, dx by ds. We're going to have dy by dt, and we're going to have dy by ds. Right? And let me shift this over to a little space. Those are all supposed to be partial derivatives, but you get the idea. And so if I go and take the derivatives here, so we take the derivative with respect to x of x with respect to t, Yeah, I guess maybe it helps if we just go ahead and write the inverses for this. So we also get, this implies that x is equal to t cosine of theta minus s times sine of theta, and it gives us y is equal to t sine of theta plus s cosine of theta. Right. So now if I take a look at dx dt, we see that it's just going to be cosine of theta. And if I take dx with respect to s, it's going to be minus sine of theta. And if I take the derivative of y with respect to t, I get sine of theta. And if I take the derivative with respect to s, I get cosine of theta. And so something to note is that the determinant is equal to 1, right? Because it's going to be cosine squared minus negative sine squared. So it's cosine squared plus sine squared, which is 1. So that just means that dx dy is the same as ds dt. So what do we get? So this changes to being equal to the integral from minus infinity to infinity, integral from minus infinity to infinity, of f of t cosine of theta minus s times sine of theta, comma t sine of theta plus s cosine of theta, and that is just plugging in x and y in here, minus e to the minus st and ds dt. So just by the selection of what we did, this ended up being t, and then we're plugging in x and y in here, right? So nothing too complicated, just plugging things in, and we should still have 1 over 2 pi out front. Okay, so something we should notice is that this only depends on t. So I can go ahead and pull it out. So this is integral of 1 over 2 pi, integral from negative infinity to infinity, of e to the minus I st times the integral from minus infinity to infinity of f of t cosine of theta minus s times sine of theta times t times sine of theta plus s times cosine of theta. Boom. And this integral ds and dt. And so if you go and take a look, this might seem really familiar. Let's go ahead and change this color, make it stand out. If we take a look a few pages ago, that is exactly that. This is the radon transform of f. So this is equal to 1 over 2 pi times the integral from minus infinity to infinity of e to the minus I st of, the radon transform of f at t comma theta, and this integral dt. Okay, let's change that to red again. Okay, so now what is that? Well, we can see that this is running through the first variable t, just doing dt here. And so theta is fixed, and so this is a Fourier transform of the first with respect to the first variable of the radon transform of f. And so, and it's pretty close. The Fourier transform itself would have just 1 over the square root of 2 pi, so we have a little bit more of constants than what we'd like, but that's okay. And so this is going to be 1 over the square root of 2 pi times the Fourier transform of Rf evaluated at, so we'll just say t theta, at s theta, because here s is our frequency. And so there we go, it's just chain of equalities, and we are done. So put a block there. All right, so that's not too bad. So this was just a couple lines, noticing that this changed coordinates, which we've already done back when we were talking about the radon transform before. And yeah, so what we're going to do now is we're going to use this to give us the filtered back projection algorithm. Okay, so let's go ahead and jump into this. So here now we're talking about theorem, well, let's switch to blue just to be consistent. So here we're talking about theorem 6.2, and this is the filtered back projection formula. All right, and so basically it says for f in short space, again, the author is just saying a suitable function defined in the plane, or well, it is defined in planes in short space, and x and y real, we have this f of xy is equal to 1/2 of the back projection of f inverse, the inverse Fourier transform applied to the norm of the frequency times the Fourier transform of the radon transform of s comma theta, again happening the Fourier transform being applied to the first variable here, and this evaluated xy. So this is a function inside the braces, and we're taking the filtered back projection, which remember is sort of an integral over a circle here. So the filtering, actually, if we didn't have s in here, then the Fourier transforms would cancel out, and we just have what we were talking about before, which is the back projection of just the radon transform. But this extra thing in here, if we put in the absolute values, it's not going to be just a blurry copy of the original function. It's actually the original function itself. And so this is the modification that needs to be made in order to guarantee the inversion process. So that's what we're going to go ahead and work with. So let's go ahead and prove this. And I can switch back to green. So we know that for f in the short space, let's say R2, we have this f of xy is equal to the inverse Fourier transform times the Fourier transform of f of xy, right? So if we take the Fourier transform of f and then we hit that with the inverse Fourier transform, well, this is just the identity and operator, and so that just gives us back f. Okay, so so that's a good first step. And if we go ahead and write that out, that gives us 1 over 4 pi squared, because remember it's 1 over 2 pi for each of the Fourier transform and inverse Fourier transform. Then we're going to have integral from minus infinity to infinity, integral from minus infinity to infinity again, of the two-dimensional Fourier transform applied to f at, say, we'll just say capital X and capital Y, of e to the I little x times big X plus little y times big Y of dx big X and dy big Y. There we go. So that's what we have. That's just expanding the definition of the inverse transform. And as you can guess, we're going to replace, ultimately, this guy with the formula that we just developed here. We'll get to that in a minute. But first, what we're going to do is we're going to change coordinates. And so we're going to change big X and big Y to polar coordinates, big S and theta, where we have big X is equal to S times cosine of theta, and Y is equal to S times sine of theta. Now this is pretty familiar from Calculus 3, But instead of letting s to be strictly positive, we're going to let s range between negative infinity and infinity. So s is in, say, we'll say over all reals, and we'll have theta is going to be between 0 and pi. Now, what that changes is it changes the Jacobian, and so it tells us that dx dy is actually going to be the absolute value of s ds d theta. Okay, so employing that, this is what we get. So we have 1 over 4 pi squared times the integral from 0 to pi times the integral from minus infinity to infinity of the Fourier transform, two-dimensional Fourier transform of f at big S cosine of theta times s times sine of theta, and this times e to the I s times x cosine of theta plus y times sine of theta. Right? So just plugging those terms in, and we end up with absolute value of s times ds d theta. All right. Now, the next step. So now that we have the variables in here the way we like them, this lines up exactly with what we saw before with the central slice theorem. So now we're going to replace this guy with this guy and move forward. So this is equal to 1 over 4 pi squared times the integral from 0 to pi and integral from minus infinity to infinity of the Fourier transform of the Radon transform at on f, where that Fourier transform only is with respect to the first variable. Then times e to the I s times x cosine of theta plus y sine of theta, same thing we had before, and then I'll leave the absolute value of s ds d theta. Now this is where it gets interesting. If you take a look here, this is actually the Fourier transform of a function, because we have this term here with the exponential. It's rather the inverse Fourier transform, and then we have all of this stuff here. We have a function here with respect to s times this, and so this here is the same as the inverse Fourier transform of another, let's put this all together, the absolute value of s times the Fourier transform of r f of s times theta, right? And so that's what we have there, and then of course we need to pull in one of these guys, this 2 pi's and here. So then what we end up getting is, because I'm getting excited, let's change color. Oh, and I should also say it is evaluated x cosine of theta plus y sine of theta comma theta. So if we go ahead and plug that in, what we end up getting is this. So like I said, getting excited, so let's change color, change purple. So we get 1 over 2 pi times the integral from 0 to pi of f inverse of the absolute value of s times f times the Fourier transform of the Radon transform of f at s comma theta, and this evaluated at x cosine of theta plus y sine of theta comma theta d theta. But this is just the back projection of this function, if you remember the definition of that. So this is equal to 1/2 pi gets absorbed into the back projection. The back projection of the inverse Fourier transform on the absolute value of s times the Fourier transform of the Radon transform evaluated at s comma theta, in this evaluated at xy. Okay. And so thus, if we compare two sides, we have f of x over here, and then we just have a chain of equalities that lead us back to where we started, which was that this is equal to f of xy. And we're done. So there you go. This tells you that if you start with a radon transform, then you can get back to the original function here. And so briefly, let's talk about this. What are the quantities that we're actually dealing with? So I'll just go ahead and copy this over. So generally speaking, you start off with a sinogram, right? Stuff like that. It goes from, say, 0 to 180 degrees, and then t goes up in this direction. So basically, remember, this is the Fourier transform of the radon. So this is basically RF that we get, is sinogram that we get. And so it says take the Fourier transform of the radon transform with respect to only one variable. And so what you do then is you fix a theta, and you take the Fourier transform of that piece, RF, here at s theta, right? And so we just do this over s. All right, we do this over t, and then the frequency you get goes in the sort of t slot. And so then you go ahead and you do that for all of these points, and then that gives you a whole array of Fourier transforms that come in your column. And then what do? You multiply. So then you take the one-dimensional Fourier transform. Is going to give you a different picture. I don't know what that picture looks like offhand, but then what you do is you multiply all those quantities by the absolute value of s. And so this is going to be with respect to s, and this is still your theta here. So theta and theta here. And so you multiply that by s. I just put dot for multiplication. Gives you something else, still with respect to s and theta here. And then you take the inverse Fourier transform, and that's going to give you another thing, 0 this time to t, where the Fourier transform, the inverse Fourier transform, was again with respect to s or t. And then finally you do your back projection, which basically we going to take an average for all these thetas that correspond, and that puts you back into f of x. And so that's the idea. So you can start with a sinogram, apply a Fourier transform to it, multiply by the absolute value of s, invert that Fourier transform, and then do a back projection, and then you're good. So yeah, and the back projection is more or less the average that you get by going in a circle over theta for a fixed x. So I think it's more or less the average you get over a curve like that or something. In any case, yeah, so that's the idea. And so between those two theorems, that connects us back to tomography and being able to invert a radon transform. And so we can start with the sinogram that you get, and we can reconstruct the original function back. And that's the whole game. And so what we're going to want to do is we want to be able to efficiently compute the inverse Fourier transform and the Fourier transform in order to compute this stuff. And that's what we're going to need the FFT for, to do basically Fourier transforms quickly. So the FFT is something that was invented by Gauss actually in the 1800s, but is reinvented by Cooley and Tukey back in the 1960s, I think. And it became one of the most highly cited papers in mathematics ever. And so the utility of this is exceptional, and so we'll want to talk about that too. yeah, but we'll go ahead and stop here, and yeah, thanks for listening. Okay, so I think I spoke a little too hastily there. I still want to talk about one more inversion method, and this is with the Hilbert transform. Now this is going to be sort of a cross between what we just did with filtered back projection and what we did well before we even started Fourier transforms when we talked about the Radon transform way back when. So what we're going to do is we're going to start with one property, and so here we're talking about the Hilbert transform. And again, we're following the method that's laid out by the approach that Feynman takes to doing this. So where do we start? Well, a good place to start is to go back and recall this property of Fourier transforms. So we take the Fourier transform of the derivative of a function evaluated at w. Then this is going to be I times w times the Fourier transform of the function f at w. Alright, so now if we transition to thinking about the Radon transform, what we can do is this. And so we're going to take a look at the Fourier transform of the partial derivative of the Radon transform of f, which is itself another function, evaluate at t theta, and we're going to take the partial derivative with respect to t. Now remember, this Fourier transform is with respect to the t variable, not the theta variable. So what we can do is we can go ahead and treat this just like the derivative in this formula here. So then what we get is I times s times f times the Radon transform of f times s theta. Okay, so now what we're trying to do is we're trying to convert this into something that looks like the filtered back projection. And so in order to do that, I need to change this from being an s to an absolute value of s. And so one way to think about the absolute value of s is that it is s times what is called the signum function of s. So if s is positive, so we'll say the signum function of s is defined as 1 if s is positive, 0 if s is equal to 0, and negative 1 if s is less than 1. Now, the action at 0 is sort of up in the air. You can make it agree with the right-hand side, left-hand side, and here they just chose to split the difference at 0. Part of the reason for that is if you actually try to take the Fourier transform of the signum function, which can be viewed as a tempered distribution, and then you try to compute its inverse transform, you'll end up getting 0 there. So they do this so it'll agree with the Fourier transform method. But in any case, that's neither here nor there. The absolute value of s is equal to that. So because if s was negative, then the signum of s would flip it to be positive. If s was 0, well, multiplying by 0 still gives you 0. And if s is positive, then multiplying s by 1 stays positive. So what we're going to do is we're going to slap signum on either side here, and this is what we get. Oh, and we're going to multiply by I. And so we're going to get I times the signum of s, signum of s times the Fourier transform of the partial derivative with respect to t of the Radon transform of f evaluated at t theta. And we're saying that this should be equal to, and this evaluated at s theta, so many arguments to put in here. S is equal to minus the absolute value of s times f of r f evaluated at s theta. Okay. So now that we have this, we can take a look at the filtered back projection. And if we go back to the filtered back projection formula, basically we said that this should be equal to f of xy. So thus far we have this plus a minus sign, and so we're going to move that minus sign on the outside here, and otherwise we're going to apply f inverse, and we're going to apply the back projection, and then that should give us f back. So that means that we have this f of xy is equal to negative 1/2 of the back projection applied to the inverse Fourier transform of a single variable of I times signum of s times the Fourier transform of the partial derivative with respect to t of the Radon transform of f at t comma theta, and this is by s comma theta, and breaking that off, and then all of this evaluated at xy. So it's quite a mouthful, and nobody wants to write that ever. I mean, if you thought the filtered back projection looked scary, I mean that's horrifying. We've added derivative signums and everything. So in order to simplify this notation, you have this transform. So for a suitable G defined on the real line, the Hilbert transform of G, which is denoted by sort of this curly h on G, is the function whose Fourier transform is I times signum times f of G. That is, for each t, we have h of G is defined to be equal to the inverse Fourier transform of I times signum of omega times f of G of omega t. And hence we have this f of xy, which is equal to minus 1/2 of the back projection of h on drf t theta dt via s comma theta at xy. Right, and so there you go. That is Radon's original inversion formula. But is couched in modern notation. And so that's that. So yeah, that's good fun, and yeah, that gives you an idea of how to get the original function back from the variety of transforms that we've been talking about. Okay, so it's getting really late now, and I think we're gonna call it. All right, thanks for watching, and yeah, we'll go back to my office.
Okay, So welcome back. So those were some quick and easy things we can do. It really wasn't that complicated, though we do have the more sophisticated background to be able to talk about the short space beyond what Feynman does in his textbook. But otherwise, it's a whole bunch of clever tricks with integrals and manipulations, and eventually you can get the filtered back projection, which is pretty handy. And similarly, you can get another inversion formula that it coincides with what Radon did back in, what was it, 1916, 1917, something like that. Anyway, thank you for watching, and yeah, have a good day.